this is the title of the presentation. My name is Jakob. I'm from the Technical University of Denmark, and the article is based on work done in my bachelor thesis. These are the co-authors, also from the Technical University of Denmark. So I'll just start with a bit of motivation on why we did this project. This is from a completely different project where we were dealing with retinal data. And we wanted to find the different anatomical retinal layers in these images. And the method we used is called ST graph cuts, where what you had to do was construct a cost image that assigned a cost to each pixel. And then the ST graph cuts method would be able to find the optimal layers going from the left to the right side of the image. So with this cost image, you would find these two curves down here. And this is quite a time-consuming process. So the obvious question that this other project made was that we wanted to do a deep learning-based method that could achieve the same with just a simple click. So what if we could let's say select here, we want the green layer, just select here, and then a model should be able to find the whole layer. So this is what our method tries to achieve. We have some sort of an image with a target label, and based on some initialization, we should complete the label, finding what layers are in the image. This is an autoregressive model, meaning we are conditioning on the information that we give our network, and each time we pass this information through the network will extend the label by 1 column of pixels, and we can do this until we extract the whole label. Now, the upside to doing it this way instead of a standard segmentation framework is that we're able to use one network that can segment data from many different domains. So it would be the exact same model that segments the bone images here and the retinal images here, even though there's a different number of labels, and the images could be any size as well. It's quite a general model, so it's just any sort of layered data that we're trying to segment. And this also makes it a bit hard to define exactly what is the target label, but we're just saying that it has to be some visually separable layers, because if they're not visually separable, of course, it wouldn't work. Now, the method is trained entirely on synthetic data, and this is what data looks like from our synthetic data generation pipeline. I'm not going to go into details on how it's generated, but it's not too complicated. It's using some textures and combining them in different ways, where we're generating the curves that separate the labels of the textures. So we can generate as much data as we want, and we generated 30,000 images. Now, how is the network architecture looking for this problem? It needs to satisfy some constraints, and the most important constraint is what we call the left label dependence, because during training, we'll give our network the complete label, such as shown here in the middle, but obviously we can't give the network complete access to this label, because then extracting the label is trivial. So let's say we're just focusing on this pixel with a black cross. This pixel, when we're segmenting it, is only allowed to see information which is to the left in the label. If it sees the same pixel in the input label, well, then the segmentation task is trivial. It's just the computing the identity. But if we make sure that every pixel is only able to see label information to the left, well, then the network will have to learn something. The way we achieve this is with what's called masked convolutions, which are like normal convolutions, except some of the information is masked out, which is shown in red here. So this 3x3 convolution would only allow information to propagate through these 3 connections. And if we stack a mask A convolution with these other types that are called mask B sequentially, well, then we can achieve the exact structure here that we want. This yellow output neuron does not depend on its corresponding input neuron. So because these are convolutions, this this label dependence is going to be satisfied for all the pixels simultaneously, which is very important. It means that all of these iterations that our algorithm computes are trained in a single forward pass, because the pixel to the right and above satisfies the same constraint. Now, this was the abstract sort of view of satisfying the left label dependence. More in practice, our architecture looks like this. We have a convolutional block with convolutions and masked convolutions, and these are separated because we are separating two different feature stacks. One that corresponds to feature stack for the image and one for the label. Because the image needs normal convolutions, we don't want to block out information in the image, only the label. So that's why these are separated, and we combine the information throughout the network. So then the network should try to predict continuing this label, and this is the simple version. In reality we also do downscaling and upscaling, but it takes a while to wrap your head around how exactly that works with the left label dependence. So I'm not going to go into detail, but we're basically just doing UNet-like upscaling and downscaling throughout the network, and still satisfying the constraint. And the architecture looks like this instead, but in practice it works as the other one. So now we're ready to look at some results on how our network actually deals with the problem at hand. These are synthetic data. And what we do here is that we've given our network the very first column of labels. So we're only telling the network essentially where do these curves start in the image, and now you should segment the rest of them. And these examples, it's pretty much perfect, making very few mistakes, and this is even quite representative of how it is on synthetic test data. On real data, the results are a bit less consistent, where we need to remember that this network has only been trained with synthetic data. It's never seen images of bones before. So here we have some MRI scans of bones, and again, we've only given our network the very first column of labels, and we're asking it to segment from left to right. And it does a pretty good job. It fails here at the 5th image, where it isn't able to capture this soft boundary between the two different porosities in this bone structure, and instead it tries to segment this very intensity-based hole in the bone. So I can see why it failed in this situation. This is sort of a hard data example that doesn't look very similar to the synthetic data. Anyway, the other examples are actually quite nice. Despite some deviations in these two first ones, I would say the segmentations are pretty good, even comparing them to the ground truth target segmentations. We've also tried it here on some retinal images, and similarly, it does well on most of the images, and sometimes it fails. Here in the third one, it fails a bit. And this is probably caused by the fact that the very first column of pixels in this image doesn't have a lot of information about the label itself. So if you're told that the orange layer starts right here, it would actually be quite reasonable to segment the orange layer as the network did. You wouldn't be able to tell that the actual segmentation we were looking for was this one over here. So this is sort of an example that goes against our problem formulation. This image isn't easy to define in a good way unless we start the segmentation at a further point, give it more label. All right. We don't need to segment images from left to right. We could also segment them in other directions. So the constraint that we only have that we're only able to segment layered data isn't as strong as you might think, because we can obviously flip or rotate an image before we segment it. We can also do transformations such as doing a polar coordinate transformation, like we've done here. We have two examples of polar data. Here we have a cross section of a log, and here we have a cross section of a Ferrero Rocher chocolate. And what we've done is we've sampled this in polar coordinates, and then we've run it through our network, and then reconstructed it in polar coordinates. And we get very nice segmentations for these Ferrero Rochers. It's less consistent when it comes to the log, but this is also quite a hard example because the layers are very unclear and there's a lot of them very close to each other. So in the bottom examples, the layers end up lining up in the Cartesian coordinates, but they do not end up lining up here, unfortunately, for some of the layers. We investigated how many pixels, columns of pixels does the network need to consistently segment images. And what we see is that the initialization size doesn't matter a lot. The error here, it only goes down very little when you give it 30 pixels or columns of pixels instead of just a single one. And for the real data, there's almost no general trend, at least not as clear as in the synthetic data, but we have to remember that we don't have too much real data to validate and test on. It's only 20 images in each of these data sets. So it would probably generally go down if we had more. One of the things we realized through the project was that data augmentations are very important when training the network. We're giving the network 2 labels, or we're giving it an input label, and then we're minimizing the distance to a target label. And these 2 labels don't necessarily need to be identical. And what we found is that if we do some sort of a deformation on the input label, but not the target label, then the network would learn to fix the mistakes that it was given. So here we're just deforming the curves in some way, the label that we give the network, and then we tell it continue the segmentation, but also fix whatever problems was in the input label. And this is good because it makes the network more robust. And we did something similar with training on network outputs, where we passed our input through the network a couple of times before doing a forward pass with gradients, sort of simulating what in essence is a recurrent neural network, and that also improved it. The main thing that would happen if we did not include these transformations is that our network would lose track of layers. It would be too confident in its own segmentation. So as soon as the network lost track of a layer, well, then it would be sure, okay, we're at the right layer. So it would just continue what looks like a layer around the part where it lost track. So in this example down here, we lose track around here in the image, in the prediction, and then the network just continues the label as if this is the layer, despite it not actually being the ground truth. So this is what the augmentations prevent. We looked at one final thing. Do we actually need to initialize the model manually? So one step in the whole segmentation process is that we start by giving the network an initialization, and this would probably have to be done by a human. So can we use our network to do away with this part of the process? And the idea we had is that we use a trained network, one that's already able to find layers quite successfully, and then we just initialize a bunch of linearly spaced positions in the right side of the image, and then segment from right to left. And what we would see is that the layers that are, or the initializations over here that are close by to the actual layers in the image, well, they would quickly converge to those layers. And the ones that aren't close would probably just move randomly. And then we would end up with a bunch of clusters of layers at the left side of the image. And when we use a confidence measure from our network, we would actually also even be able to tell which of these clusters does the network think are actual layers. So in this situation, we would want the 2 green ones. And if we correctly selected these 2, well, then we could do the actual segmentation starting here and here. And in no part of this process would a human input be needed. So we tried doing this, and it actually turns out to be quite successful. On synthetic data, we only saw about a 5% loss in performance. On our error measures, we had a few different error measures, but in general, the segmentation is very successful and rarely damaged much. In this situation down here, we only find 2 of the 4 layers in the ground truth, but some of them are quite hard to find. It even fails in the situation where it is given the initializations. Down here in the bottom layer, we only find 4 out of, or in the bottom image, we only find 4 out of the 5 layers that we were supposed to segment. But generally, there would be a very little loss compared to when we did a manual initialization. Here we have some examples from real data. We lose quite a bit of performance on real data. Unfortunately, it's not as consistent, and this is mainly caused by the fact that we did not train on real data. It's not robust enough to actually find layer initializations by itself. Usually, sometimes it can do it, as we can see in maybe the top example, and other times it will find some layers, as in the bottom 2 examples here, but also find some things that aren't supposed to be segmented. So the automatic initialization isn't too useful when actually dealing with real data. Anyway, that's what I have to say.